Welcome back, everyone, to the fall semester. This is our first installment of the PALS seminar today. I'm glad that you all joined again. And today, Nik Ruskuc from University of St. Andrews is going to start us off with congruence diameter of semigroups.
Thank you. Please. Hello, everybody, and thank you, Peter, for the introduction. And even more importantly, thank you for hosting me yet again here in Boulder. It's really good. It's always good to be back in Boulder, and I'm having a very good and hopefully productive time. Thank you also, everybody who joined remotely. What I'm going to talk about here is, in a way, a continuation. I was just thinking, but I was too lazy to check up. A year ago or 2 years ago, I spoke about finiteness conditions of semigroups to do with their actions. And in a way, this is like the continuation of that talk, where we will go into one of the properties in a bit more detail, and I'll report on some more recent findings. Nothing to worry about. I'm not assuming any prior knowledge, and also there will be no test at the end, so people can relax. Also, the people involved are very similar to who they were last time, but not entirely. So let me introduce the characters in this game. Is there a way in which I can actually see my slides? Probably not, right?
I think you can remove you're talking about the screens, right?
Yes.
Yeah. If you move your mouse cursor above, yeah.
Oh,
yeah, there's a button
like this?
Yeah. Probably that.
Thank you. Fantastic. So this photo was taken a couple of years ago at a workshop that Vicky Gould, who is on the left in this picture, and I organized in York under sponsorship of EPSRC, which is the UK research funding agency. And it's one of my, I don't know what was the right adjective, my dearest or mathematical occasion that I really have enjoyed so much. It somehow stayed in my mind as something quite special. It wasn't really a conference, it was gathering of people, and we did some talks, and we sat around and we did maths, and lots of papers came out of it, and there were lots of young people involved, and they all seemed to have good time. And so I thought it was great, and I hope that'll get repeated once. Among other things, what we did was work on an advanced draft of the work that I'm going to tell you about here. And it was James East from Western Sydney, who is the second person from the left in this photo, who said we really ought to take a photo of us for the future PR purposes. And that was very foresightful of him, because I never keep my photos. And a few days ago, as I was finishing my slides, I thought it would be nice to show a photo. And I emailed James and I said, do you by any chance have, I was thinking individual photos of the participants, of co-authors of this work. And then he very smugly said, of course I do, don't you remember? And so that's the photo. So in addition to Vicky and James, there is me, and then next to me is Tom Quinn Gregson, who is currently affiliated with York, and Craig Miller, who is my former PhD student, who is also currently in York. And the work that I will tell you about is distributed across 3 papers, and the papers have various subsets of these authors as co-authors. And I'll give some indication, but I generally find that when I give talks, I somehow seem to go much more in the direction of mathematics and much less in the direction of constantly repeating people's names. So I, in advance, apologize. I don't want to offend anybody, but I think my mind will go in the direction of mathematics. There will be references at the end, so it'll all be fine and clear. How do we know? We need to, okay, maybe now we're good. Yeah, okay. I'll start with a little prelude, which is almost not really necessary, but at the same time, it's so cute. And I thought it was a good place to start it. And if sort of mathematically, as something happens mathematically, this is the only thing you remember from the talk, I'm still very happy. I find it very cute. It's super elementary. Think about the full transformation monoid on natural numbers. So this is simply all transformations, all mappings from n into n, full mappings, everywhere defined. Operation is composition. I will write my mappings on the right. And this monoid, like any other monoid, acts on itself on the right by right multiplication. If you haven't encountered monoid acts, semigroups acts before, they're playing a kind of underlying role in this talk, but not the main role. So don't worry about it, but think about them. What modules are for rings? Semigroup actions are for semigroups. They're somehow mathematical expression of different ways in which a semigroup can act. And if ring acts naturally on something like an abelian group, semigroup acts naturally as a semigroup of mappings. And that's kind of what you think. And somehow the most natural act associated with every semigroup is semigroup itself acting on itself on the right or on the left if you want, but here I will err on the right side. Okay, so now we have this action, we can take it square. What is the square of an action? Well, the elements are pairs of elements acted upon, which are the elements of my semigroup, but they're acted upon by a single element which acts diagonally. So you get a single toe acting on a pair, and it just multiplies both elements in the pair kind of simultaneously. So this is different from the direct product of monoids, where you would take two pairs and multiply them component-wise. This is weaker. Okay, so we now have this Tn acting on itself on the right. Okay, now let's do some really sort of high school math. So take these two mappings. Let's say our natural number starts with 0, just because they do for the next 5 minutes. Take the map 2x and take the map 2x plus 1. What these two maps do, they take n and kind of split it into two, like, right? The image sets are completely disjoint and cover n, but that's not so important here. Okay, now suppose somebody gives you two mappings, gamma and delta, arbitrary, and define a third mapping, which we'll call tau, which on even numbers acts as gamma, and on odd numbers acts as delta. So in this way, you have kind of, in this tau, you've encoded two mappings at the same time. Just because your set is infinite, you can do that. No, nothing magical there. But now if you think, well, if you perform these compositions, if you do x alpha tau, you go 2x tau, and that gives you x gamma, just by the definition. And similarly, x beta tau gives you x delta. Or in other words, in our notation from the previous slide, if you multiply the pair alpha beta by a single transformation tau, you will get the pair gamma delta. Okay, so all very easy, but kind of cute. And it actually has quite a lot of consequences, which, like, this is a weird thing which I kind of encountered a fairly long time ago. And it's quite cute. And then it turned out to be of importance in various areas where I didn't particularly expect it to arise. And so it's followed me somewhat. Okay, so let me give you some different interpretations of what we have seen. Well, first of all, I told you, or I showed you, that the act Tn cross Tn can be obtained by taking a single pair and acting on it with the Tn. In other words, the act Tn cross Tn as a Tn act is monogenic. It's generated by one element, this alpha beta that I constructed. a historical note, this was first observed by Bullman, Fleming, and McDowell in 1989. I think it's a monthly American whatever it's what's it called? American Mathematical Monthly, is it? Problem and solution, basically, this little construction. And as I said, it turns out to have applications for various things. In particular, in my case, I encountered applications for fine generation and presentability of read products of monoids and of power monoids. That takes us somewhere else. I'm not going to dwell on it, but it has links. Another interpretation of what we have seen is that this direct product of two TNs is actually isomorphic to the TN considered as an act. They're both isomorphic to the free TN act on a single element. And then the viewpoint that interests me here, which may involve some words that perhaps you don't immediately relate to. I will introduce, but let me just spread it out first. If you take alpha beta, and if you generate the right congruence by the pair alpha beta, the right congruence on the monoid Tn, and I'll tell you in a second how you do that, but certainly to generate right congruence, at the very least, you take all the multiples of this alpha beta, and that already gives you all the pairs. So the right congruence generated by alpha beta is actually the full congruence on Tn. So the biggest possible congruence can be generated quite quickly. Okay. Not only that, but any two pairs can be obtained from this generated pair like very quickly. Just one single multiplication and you are there. And this is kind of the root idea behind a more general concept that I'm going to talk to you about today. But now I'm going to step back and be a little bit more systematic and introduce properly the notation and the concepts that we need. And then I'll tell you what the things are, what the results are. But before all that, I'm going to pause just in case there are any questions, and I'm going to take a sip of water.
You have uppercase Alex on the previous slide. Are they all Blackboard? Or do you mean the transformation?
Oh, I made the same mistake in Denver, didn't I? Except that in Denver it was for symmetric group and it occurred once, and today it's the full transformation monoid and it occurred twice. Why are you on my case, Charlotte, today?
This time I was just trying to be helpful.
Like you totally are. I'm just joking. It's all good. Thank you very much. I'll correct after the talk. Yeah, very good. Okay. So right congruences are important for this talk. Right congruence is an equivalence relation which is right compatible. If you have a pair, you multiply it by a single element, you will get another pair in the relation. Their importance in semigroup theory is they're intimately connected with acts, but I told you I'm not going to worry about acts too much, but that's where they arise. In particular, if you have a semigroup and you have a right congruence, then the semigroup acts on the quotient set, on the set of all equivalence classes. That's essentially what this definition says. When S is a monoid, actions arising in this way exhaust an important collection of actions of S, namely all monogenic actions, all actions that are generated by a single point, which is semigroup equivalent, semigroup version of what in group theory you would call transitive. Congruences can be generated, so you can anticipate what is on the next slide. First of all, if you have a semigroup and you have a set of pairs, then you can talk about the right congruence generated by this set of pairs, and it will be the smallest right congruence which contains all the pairs in the set. How do you convince yourself that such a thing exists? Well, you say I intersect all the right congruences that have this property. I do little exercises which say intersection of right congruences is a right congruence. I convince myself that there is at least one right congruence containing the set, which is the full congruence, and you get there. But then you want more. Then you want to say, but how do I lay hands on this thing, the right congruence generated by the set? And here is the description. And it's again what you would expect. So two things are in the congruence generated by a set if you can go from one to the other by a sequence of the following form. So here is what we have. This is a typical instance. We have this C1T1 and D1T1. So and C1D1 is a pair in the set. So what we are allowed to do is to find a left-hand side of a generating pair and replace it by right-hand side, but only as a prefix in a product, or vice versa. We can find the right-hand side and replace it by a left-hand side. And we keep doing that, and we are allowed to do it only finitely many times. And all the pairs that we will reach like that will be precisely the right congruence generated by the set. This you can prove from the first principles, or you can actually view semigroup actions as, or you can view semigroup actions as algebras and with unary algebras, and then use the general theory of generating congruences on arbitrary algebras. Either of those will give you this. So entirely standard. How I want you to view this is I'm connecting A and B via something. So there is some kind of connection going on. There is a path. I'm going from A and I go and I do something and I do something and I do something. Eventually I arrive at B. Because this is the motivation for the notion of diameter that I'm going to introduce on the next slide. Okay, so now we come to the diameter. Okay, so I start with a semigroup and I look at the full relation. So the biggest equivalence on my set, on my semigroup. And I consider the full relation as a right congruence. And I ask myself, how can I generate the full congruence? Now, for different semigroups, the answer will be different. But I'm particularly interested in the cases when I can generate the full congruence finitely by a finite set of pairs. So from now on, we just think about those semigroups. I'll give you some examples. Okay, so suppose I pick a finite generating set for my right congruence. My congruence is the full congruence. So now this means that I can go from any element to any other element by doing these elementary transformations that I showed you on the previous slide. And I ask, and this is actually not entirely precise, for any two elements, I ask, what is the shortest way I can go from one to the other? And then for all the pairs of elements, I say, what is the longest the biggest number I get? This will be the diameter with respect to the generating set Y. So what are the 2 points that are farthest apart with respect to Y? The answer can be infinite, even though all the distances are finite, but maybe there is no supremum. That can perfectly well happen. Okay. And now I quantify over all finite generating sets. And I say, what is the smallest diameter I can get with respect to a finite generating set? And I call that the diameter for the semigroup. So this is like min, max, min definition. Fortunately, as I told you, we've seen all the mathematics that I'm going, there will be a tiny bit of mathematics later on, but so just remember it's a min, max, min, and it's some kind of distance in some graph that you can define, or metric space. it's very important. You can't do this for infinite sets, really, because at the point where you allow arbitrary generating sets, then the answer will always be 1, because you will always take S cross S as your generating set, and then the distance will be 1, and nothing to play for. We'll call this D of S the diameter of S, and then slightly controversial bit. If semigroup has finite diameter, we'll call it pseudo-finite. I hate the name. I think I already confessed that I hate the name, but it's there. Some other people called it pseudo-finite. Some people even like it. I don't. And example is what we saw at the beginning. Tn has diameter 1, because I can take my generating set alpha beta that I constructed. From the generation theorem, it tells me that I get the full congruence from it. And from what I showed you, alpha beta tau equals delta gamma means gamma delta, it means I can reach any pair in a single step. And that means that the diameter is 1. So what we are seeing in this example is that we can have infinite semigroups, in fact, very infinite semigroups. Tn is not even countable. Tn is size of continuum, which can have very small diameter, which maybe to begin with wasn't immediately what one would expect. Let me give you some context for this concept. Pseudo-finite monoids were introduced by White in 2017. Quite far away from semigroups. It's his work on semigroup algebra, I mean, quite far from combinatorial semigroup theory, let's say. And it's more kind of in the algebra world and considering the connection between semigroup and its semigroup algebra. Kobayashi in 2007 considered the weaker property of full congruence being finitely generated. Our property is full congruence finitely generated plus I can reach from any element to any other element in a bounded number of steps. If you remove this other condition, you get the condition of finite generation for the full congruence as a right congruence. This is equivalent to the homological finiteness condition FP1. Again, I'm not going to, different topic, but seems to relate to things. More detailed study of this property of delta nabla S being finitely generated can be found in a paper by these 4 people from 2019. Lots of information, structural information, constructions, examples, things like that. For a group to be pseudo-finite is really not very interesting. It's equivalent to being finite. This more general property of nabla S being finitely generated is equivalent to being the group being finitely generated. And then when you introduce the bound on the length, you get precisely finiteness. Easy exercise. In fact, you can generalize this. You can generalize it for some kind of properties here that don't make much sense, but weakly left cancellative and L star simple semigroups. Never mind, like you can go from being a group to being one side to being left cancellative, or to being somehow simple on one side. Groups are, as semigroups, groups are always simple. They don't have ideals. Okay, or even one-sided ideals. Fine. So the morale of this is there are other semigroups for which pseudo-finiteness is actually equivalent to finiteness, hence the name. Like somehow when you see the property, and if you're a group theorist, you say, this is actually just a very weird way of saying you're finite. And then somehow in semigroup theory it isn't, and yeah. So, and we said there are infinite examples. We've covered that. Some more context. Tn is pseudo-finite because we said it has diameter 1. In fact, diameter 1 is equivalent to the diagonal act being not necessarily monogenic, but finitely generated. Finitely generated would be enough for the diagonal act. It is a finiteness condition. Certainly all finite semigroups are pseudo-finite of diameter 1. I can take S cross S as a finite generating set. This is quite cute. Vicky Gould has convinced me of this about 3 times so far. And every time I forget, and then she reminds me. If you have a finitely generated semigroup, then it has finite diameter if and only if you look at the Cayley graph of the semigroup. So this is the graph of the semigroup generators acting on the semigroup. So you look at the Cayley graph, you erase the directions, so you get an undirected graph. And so semigroup has finite diameter in our sense, if and only if the Cayley graph, underlying undirected Cayley graph, has finite diameter in the usual graph theoretic sense. And the 2 diameters are not equal, but they're closely related, factor of 2 or something. You need to do a little bit of funny dance, but I'm not sure. And then I always say, but why are we not then talking about things for which Cayley graph has this property? And then Vicky again reminds me, but there are non-finitely generated semigroups which have finite diameter, like Tn. Tn is huge, can't be finitely generated. Okay. Just a little bit more elementary maths, and then we go on to the examples that I wanted to show you. If a monoid, so if I have an identity, and if I have a 0, then the whole question of diameter sort of collapses. I have small diameter. I have diameter at most 2. And the reasoning is as follows. Take this pair, consider this pair, 0 and 1. Then I can do an elementary sequence from an arbitrary A to an arbitrary B as follows. I can express A as 1 times A, then replace 1 by 0. I get 0 times A, but 0 times A is 0, and then I can reverse and get to B. And so I did 1 step here, and I do 1 step here, and I have 2 steps, and my diameter cannot be bigger than 2, but maybe it can be smaller if the diagonal act is finitely generated, which it can be. A small generalization of this argument here gives you something that is perhaps a little bit more useful when you look at real-life semigroups. Let me have a monoid, and suppose that it has an ideal, like a 2-sided ideal, and suppose that this ideal has finite diameter. Then essentially mimicking this process, I can go from any point down into the ideal, muck about in the ideal itself, and then swim up again in one move. And that gives me the diameter of the semigroup certainly being finite and no bigger than d of I plus 2. So if I have a monoid, if I find an ideal that is better to work with, I can then kind of link them in some way. Right. Maybe I go one more slide because it contains what we're going to discuss now for the rest of the talk. We've discussed Tn. Let's visit some other well-known natural semigroups of transformations and ask, what is your diameter? So let me first introduce, this is a selection from what we did in the paper. In the end, I'll show you a table which contains everything we did in the paper. And so let me pull out 3 significant transformation semigroups. Partial transformation monoid is like the full transformation monoid, but you allow your transformations, your mappings, not to be defined on some points. So they are only partially defined. Full transformation monoid we have already encountered. It's a submonoid of PTX consisting of all mappings which have the full domain. And let's consider IX, the symmetric inverse monoid, consisting of all partial transformations which are 1, 1 on their domain. Of course, maybe you expected me to have Sx, symmetric group, because why not? It's a famous transformation monoid. But we already said a group is pseudo-finite if and only if it is finite. So Sx is not finite, and so no point even writing. Well, we saw already that Tx has diameter 1 because of the diagonal act. The story is the same for Ptx, the same proof, pretty much. And Ix doesn't have a finitely generated diagonal act, as it happens, but it does have a zero because the empty mapping is a partial bijection, and it features as the zero of that semigroup. And so Ix is diameter 2. Not very interesting, I would say, all this. Like somehow, yeah, okay. So let's look now at a kind of second generation. Let's look a little bit deeper into Tx and Ptx and fish out some interesting monoids. So here are a couple. Let's look at all the full injective mappings. So full domain and injective. That's certainly a submonoid of Tx. This monoid actually has a minimal ideal. This requires a little bit of work to prove. It's called the Beer-Levy semigroup. It's a very cute semigroup, lots of interesting properties. It consists of all injections, all full injections, whose complement of the image is large. It's as big as it can be. Certainly, if you have an injection on X, its image will be large. You have no choice about that. It'll be the same size as X. And this is saying, but also the complement of the image will be as large as possible. So that's the minimal ideal of Inj X. This semigroup is, as it happens, right cancellative, which hopefully we know what we mean, and right simple, meaning it doesn't have any right ideals. It's the only right ideal of itself. For Beer-Levy semigroup, we can prove that its diameter is 3. And I spent a long time, I really would have liked to, there is some really nice combinatorics, infinite combinatorics going behind this, particularly, you have to do 2 directions. Of course, you have to show that it's at least 3 and at most 3. Proving that if you have an arbitrary finite generating set for the full congruence in BLX, you really need to make 3 steps, involve some really nice combinatorics where you sort of somehow have some systems of sets which you need to visit as you go along. And it just has to be in 3 steps. It can't be in fewer than 3 steps. So I couldn't quite see a way of conveying this other than telling you a story like this. As a consequence of this, remember what I told you about if you have an ideal and it has finite diameter, which it does, then I know that my original semigroup, which is Inj X, will have finite diameter, and I get an upper bound, and it's 3 plus 2, and it's 5. And then we asked, what is actually the diameter of Inj X? And as it happens, it's 4. Okay, so some numbers are starting to appear. I guess that's where, like, I'm not trying to say you can see it. There is work involved. It was good fun doing it. And some finite numbers are appearing. Okay, so now that we've done injective transformations, you know what I'm going to do next. I'm going to say surjective transformations. Okay, so surjex is all the mappings in Tx which have the full image. Everything is in the image of the mapping. It has a minimal ideal again. It's called the dual Beer-Levy semigroup. It consists of all surjections which have large pre-images for every point. A pre-image of every point has the size of the entire set. So in other words, kernel is a partition of X into X blocks of size X. Okay, there are those things. But in fact, I shouldn't have taken you on this little detour. Well, okay, In fact, I should, but let's go back. As I told you that this one was right cancellative and right simple, I should have told you that this one, DBLX, is left cancellative and L simple. And then there was a previous slide which said, well, if you have one of these properties, then your diameter is infinite. You're not pseudo-finite. You can't be finitely generated. So that shows that DBLX is not pseudo-finite. And likewise, SurgeX is not pseudo-finite either. And in fact, I now realize I'm not entirely precise. The full relation is not finitely generated even. So it's not even that it's not pseudo-finite. The full relation is not finitely generated. Okay. So, okay. But now that I said surjections, that reminds you that there is some kind of left-right duality about semigroups. And why was I sort of writing my mappings on the right, and why I was acting on the right, and why I was telling you about the congruences on the right? And the simple answer is just to make things simpler, because I didn't want to carry left-right all the way through, but I could have done everything I told you on the left. So I could have defined left congruences. I could have told you how to generate left congruences. I could have defined left pseudo-finite, which would mean, and that's a mistake, the full congruence finitely generated is a left congruence and finite lengths of chains between any two elements. I could have told you then the minimum of those numbers is the left diameter. You can kind of fill in the blanks in your head. We now need two pieces of notation because now we have two diameters. We have left diameter, we have right diameter. It won't come as a surprise to you that the two are different. No reason to expect that semigroup will behave the same on the left and the right. That's somehow one of the basic tenets of semigroup theory. But anyway, now we have two diameters. Things become more complicated. And then you travel the same path as you did, but very quickly. Left diameter of full transformation semigroup and PTN, they're both one. There is a dual of Bullman-Fleming-McDowell argument, which shows that left diagonal act of Tn is also cyclic. It's more complicated than like Tn is different, like really different on left and on the right. On one side, you're dealing with images. On the other side, you're dealing with partitions. And there are two levels of mathematical complexity. So a little bit of tiny kind of fun and excitement. But results are the same. Both are 1. For IN, it's 2. Injex and BLX don't have finitely generate. So everything now gets dualized. Beer-Levy and Injex, they don't have the full congruence finitely generated as a left congruence, but the dual Beer-Levy semigroup semigroup has 2. So what for Beer-Levy was 3, for dual Beer-Levy happens to be 2. That means that for SurgeX, again, using the ideal lemma and so on, I get bound of 4. And then we say, what's the result? And the result happens to be 4. All of that is great fun when you're doing it, but like now they're just numbers. Yes, Peter?
When you write Tn, do you mean T of the natural numbers?
Yes, I do.
Set
Yes.
or arbitrary?
No, it's like, this should have been Tx. Tx, PTX, Ix, like X here and X here. Arbitrary infinite set. Yes. Yeah. Okay. That's kind of a bridged story. The full story is somehow contained in this table. For some monoids in this table, I even forget what they are, particularly Ajax and Kx. So we can look up. There is one that is even bigger than PTX. That's binary relations. Not interesting. Diagonal act finitely generated. So nothing super exciting happening. Maybe worth highlighting. Otherwise, James East, if he's listening from Sydney, will be not pleased with me. are these two last one. Strictly speaking, they're not semigroups of transformations, they're semigroup of partitions. And in some long and distant past, I've talked about partition monoids in this seminar in some completely different context. And we get some like very small numbers for them as well. Okay, so lots of semigroups that we have looked at in the paper. Let me finish with some questions. The key question for me is, why are all the numbers that appear so very small? Which is not really a mathematical question, but that's really what interests me here. Why are they small, and why is 4 the biggest that appears? Do there exist semigroups of arbitrarily large finite diameters? Vicky and I think that the answer is yes. We think we have a construction, but it hasn't been written up properly. So take it with as a probability distribution rather than a claim. But at best, it will be a construction. It will kind of say, here is a thing, and then do some maths to show that it can be arbitrarily large, the diameter. It's finite, it's arbitrarily large, doesn't hit all numbers. Can we get any number as the diameter? Don't know. But perhaps more interestingly, if anybody has an intuition for a natural semigroup that might have a finite but big-ish diameter, what would that be? We dug quite deep into these transformation things. They all have small diameter. My very intuitive feeling, which I can't transfer into maths, is that somehow they're very full, all these monoids. There are lots of mappings, all the mappings of a certain kind. And then this property is either enough to give you finite generation, in which case, because you're taking them all, you will get small diameter, or else it's just a not strong enough property and you can't reach everything in finitely many steps, and so you fail and you get infinite or not applicable or whatever. I can't turn it into maths, but would be interested going into the future. Let me now interrupt the questions and can we doing with time, Peter?
That's 8 minutes.
Poof. Okay. Another really, really nice story. It actually doesn't involve, well, it involves me because I talk to all the people, but the paper doesn't involve me. It's a beautiful result. Very quickly, so you can play the following game. So far, we have taken an unstructured set and looked at all the mappings of certain kinds on that set. Another game you can play is take a structured set, like maybe an ordered set or a graph or something like that, and look at all the endomorphism, all the mappings that preserve the structure. Okay, so people who are involved in this, which I will say in a second, did that, and they did it for chains. So you take an infinite linearly ordered set, and you look at all order preserving mappings. They form a monoid, which will denote end C. My clicker is becoming temperamental. An endpoint of a linearly ordered set will be a minimum or a maximum if it exists, just a word to denote either of those two. And I will say that my linearly ordered set is endpoint shiftable if it has an endpoint which I can remove, and what remains is a homomorphic image of the original set. Just a few quick examples. This doesn't have endpoints. This is linearly ordered set Z, no minimum, no maximum. Natural numbers have a minimum, have no maximum. If I remove the minimum, I get another copy of natural numbers. So certainly isomorphic, not even homomorphic image, isomorphic. So endpoint shiftable. If I take Z and add minus infinity, as it says here, but not here, I add minus infinity to it and let the rest of Z stay the same, then if I remove this point, then I can't map the whole set onto this, because minus infinity will go somewhere in what remains is Z, minus infinity goes somewhere, everything else goes above, but I've missed an awful lot of my set. Okay. So people involved here are East, Gould, Miller, and Kuhn-Gregson. And the theorem is, you take an infinite chain, it will have right diameter equal to 2, if and only if it is endpoint shiftable. It will have, otherwise, it will have right diameter 3, and it will always have left diameter 2. I think it's just great. It's just very beautiful. Like, why this kind of easy order theoretic property, easy but not kind of very common order theoretic property, translates into this numerical dichotomy here. And why is there nothing similar on the other side? I think it's a lovely result. Leads me to my second set of questions. You can play this game more, like take other structures, take some graphs. Here I'm proposing to look at specific graphs like random graph and maybe random tournament or countable Boolean algebra, just because countable Boolean algebra is on my mind because of Peter these days. But you can also play a similar game as before, like take all graphs and say, put a condition on the graph which will ensure that diameter is finite or the diameter is small or something like that. You can do that. I believe that, I'm not entirely sure, but I think that people here are actually working further, maybe on posets in this direction. Maybe you want to look at continuous mappings. That was just a thought that came to my mind as I was writing the talk, so not very well founded, but maybe there is something in it. And something that Craig Miller has introduced, and I think it's a lovely property, but we haven't quite found the right inroad into it. So we looked at semigroups where the full congruence is finitely generated in a bounded way, diameter finite. What if we impose the condition that all right congruences have this property? So that would be like a very strong finiteness condition on semigroups. Does it give something interesting? Not all right congruences. All right congruences is finite index. So think if you move a little bit away from the full congruence, you still retain this property. I think it's a very nice condition. Don't know quite what to do with it at the moment. And this is where I will leave you. These are the main references. And thank you for listening and happy to take the questions.